Hi everyone, welcome to Bangalore Theory Seminar Series. We are excited to have Dr. Nithin Varma today as our speaker for the talk titled Improved Sublinear Algorithms for Testing Permutation Freeness. He is an assistant professor in computer science at the Chennai Mathematical Institute. Prior to this, he did his postdoc in Department of Computer Science in University of Haifa and his PhD from Boston University in 2019. Interestingly, he also has a connection with IISc. He did his internship here around 10 years ago. His research is in the field of algorithms with a focus on sublinear time algorithms, randomized algorithms, and approximation algorithms. He has also won the Best Paper Award at the ICAL this year. His talk today would be about that work. With this, I hand over to him.
Thank you, Rishikesh, for the kind words. Actually, I did 2 internships with Sunil at IISc, 2 summers. Okay. Yeah, so I will be speaking about our recent work on sublinear algorithms for testing pattern freeness, jointly with Newman at University of Haifa. And since there are not many in the audience, so we can go at a slow pace, and you can ask questions, stop me at any point if you want clarifications. So this is going to be a kind of a high level talk in some sense. I'll be doing a bunch of hand waving of our techniques, but feel free to kind of stop me and ask me more detailed questions. That's fine. Okay, so let's get to the material. So I'll first define what are ordered patterns in arrays. So our input objects are arrays of length n. Now let's assume that you also have a permutation pi of length k. It's a bijection from integers 1 through k to 1 through k. So it's a permutation, right? Now I say that this array has a pi appearance if there are k indices, k array indices, such that somehow respect the ordering according to the permutation, such that these array values and these indices respect the ordering according to the permutation. I'll make this clear with examples. And the array A is pi free if it has no pi appearance. Okay, so now let's see some examples. So consider this, very simple small array of length 5. It's a real valued array, or maybe rationals. Now, this array, maybe before showing, I'll actually tell you, this array definitely has a 2-1 appearance. So 2-1 is a permutation, right, of length 2. It definitely has a 2-1 appearance. For example, 198 form a 2-1 appearance because the values are decreasing. Or 101.2 for that example, for that matter, or 723 and 5.88, right? This array also has a 1 3 1 3 not 1 3, maybe 2 3 1 appearance. An example would be, let's say, 100, 723 and 5.88. These 3 things together, 100, 723 and 5.88. Right? This forms a 2 3 1 appearance because 2 is less than 3 and 3 is greater than both 1 and 2, that way, right? So the relative ordering of these array indices is identical to the relative ordering of that permutation. This is what I mean by having a pi appearance. So here are a bunch more examples. This has a 213 appearance. Can somebody maybe point out a 213 appearance?
$98 1.2.
Right. No, so this will not be a 213 appearance.
Sorry.
198, 723.
Yes, this will be a 213 appearance, right? This is just, these examples are just to kind of like get into your head, because it's a bit of a strange notion when you first see it, right? That's why we have some examples. Bunch more examples. So the array, you can see that there are 312 appearances, 3412 appearance, but there is no 4321 appearance, for example. So you can say that this array is 4321 free, because there are no such appearances. Now, so the main problem we study is the following. Given an array A of length n and a permutation pi, is the array pi free or epsilon far from pi free? And by epsilon farness, this is what I mean. An array is epsilon far from pi free if the Hamming distance of this array to every pi free array is at least epsilon n. In other words, the array, at least an epsilon fraction of the array values need to be changed in order to make the array pi free. So it is clearly it is a relaxation of the exact question of asking whether the array is pi free or not. So it's a relaxation, and this is called a property testing relaxation. Right? It's a standard question. This type of question is really well studied in the field of property testing. So this is a property testing problem for the property of pi-freeness. So this is a property testing problem. And this is the problem that we study. Now, this is a generalization, the specific problem of pi-freeness is a generalization of testing whether arrays are monotone or far from monotone. Because monotonicity is equivalent to 2-1 freeness. So an array is monotone or sorted if it has no 2-1 appearances, right? If there are no two indices such that the left index is larger than the right index. And these indices need not be adjacent, right? So it's a clear generalization of the monotonicity testing problem, which is really well studied in property testing. So it's a direct generalization. And the motivations for considering this sort of pattern freeness, initially when it was studied, so the motivation was stated to be understanding, motifs in time series or stuff like this. So essentially, these kind of questions are asking about trends in, long sequences of data, long-term trends in some sense, right? That's what we are trying to understand here. And this is one type of such question, one such type of question. So the study of pi-freeness testing was initiated by Newman, Rajendraprasad, Rabinovich, and Sohler in 2019. And it was studied extensively for monotone permutations. That is permutations of the form 1, 2 up to k or k minus 1 up to 1. A special case being monotonicity, right? So when k is equal to 2, this is really monotonicity. So now,
can you repeat, like when it's monotone, the array is fixed, right? So what are they testing there?
So whether the array is monotone or whether it is epsilon far from monotone.
Okay,
the property of monotonicity.
Okay, they were testing monotonicity earlier.
No, it's not. So there are lots of monotonicity testers, and then Newman et al. Initiated this study of pattern freeness testing, which is a generalization of monotonicity. And most of the follow-up works concentrated on monotone patterns. This is not, see, for example, checking for 3-to-1 freeness is not identical to checking for monotonicity. This is not equal to monotonicity or sortedness, right?
Got
An array that is 3-to-1 free, does not necessarily be sorted. It can still have 2-1 patterns, right?
Yes, got it. Thanks.
So yeah. So point is, this pattern freeness questions has been studied for monotone permutations mostly. And there is a all of these works culminated in a big of log n query tester for monotone patterns of constant length. So the resource that we are trying to optimize here is the query complexity or time complexity. So you assume in the computational model, you assume that you have Oracle access to this array and you want to quickly check whether the array is pi free or epsilon far from pi free. Because if you can see the whole array, it's a trivial problem, right? Yeah. So there is a.
We can see the whole array. Like, is it doable in linear time, or will it take a lot of time, or exponential?
So exact checking, there are linear time algorithms, as far as I know, at least for monotone patterns. So this is actually a well-studied question. Even earlier, this has been studied. When you can see the whole array or counting the number of specific types of patterns, all of these have been studied actually. So in the property testing regime, we assume Oracle access to the array, and we don't want to look at a lot of indices in the array. So this is very efficient. You can just look at log n indices, big of log n indices, and determine, right, and test. Now, for coming to arbitrary permutations, Newman et al. Showed that you can construct a polylog n query tester for arbitrary permutations, but of length 3. For monotone permutations, we knew for any constant length, big of log n. But for arbitrary permutations, only up to length 3 was known. Rather, like very efficient testers were known only for length up to 3.
So is there a impossibility result for constant time, or
Impossibility for constant time? Yes, because already the problem of monotonicity, testing monotonicity, there is a tight lower bound of omega log n. So log n is the best you can anyway hope for. You cannot hope for anything better than log n. Yeah. So constant queries is out of the picture.
So this lower bound is for 1, 2, 2, 1, right?
Right, 2-1, yeah. And it's a special case of the more general problem, right?
I'm guessing here you get like with high probability statements and autolog.
Sorry, Ramesh, I could not hear that.
Yeah, so I'm guessing here you get like with high probability statements with big of log n.
Yes, all of these are randomized algorithms and we are showing high probability statements. Yes. Yeah, these are all randomized algorithms. And these query complexities are high probability query complexities.
are these testers one-sided? Sorry. Or
yes, these testers are all happen to be one-sided error testers, but the lower bound I mentioned for monotonicity is a two-sided error lower bound, right? So the main open question that resulted from all of these works were, what can you do for arbitrary patterns or non-monotone patterns of constant length? Can you say something? In fact, we can say something. Something has been said. That's how I should put it. So for non-adaptive testers, Newman et al. Plus BCLW19 together jointly, so in a sequence of works, if the so they've proven a nearly linear bound for testing pattern freeness of patterns of length k when the tester is non-adaptive. A tester being non-adaptive, I mean the tester makes all of its queries in advance before seeing the answers to any of its queries. This is what I mean by a non-adaptive tester. All the queries are decided in advance. So my point is there is a tester that can test for arbitrary patterns of length k, but whose query complexity dependence gets worse and worse as k increases. And yeah.
Question here. So the testers on the previous slide, like were they also non-adaptive?
So this one?
No, yeah.
This is adaptive actually.
Okay.
And it was also shown that you cannot really do any better for non-adaptive testing. That is, there are permutations of length k. For every k, there is a family of permutations such that every non-adaptive tester testing for pi-freeness for permutations from that family has to make omega n to the 1 minus 1 over k queries. This bound is tight. So with non-adaptivity, you cannot hope to do anything better than near to linear. It's sublinear, but very close to linear. This is not the kind of complexity that would be truly sublinear, right? In some sense.
This lower bound, is it true for all k?
Yeah, it's true for all.
Let's say if k is n, doesn't it get easy? Like, the entire pattern, right? You have to check whether the entire pattern is mapped to this or not.
When k is large or k is small?
K is n. Let's say k is n.
Yeah.
You have the entire pattern, like a permutation, and you have to check whether the given array is this permutation or not, right?
Right.
Isn't that easy? That looks easy, right?
That's
No?
n. You actually have to check the whole thing, right?
Yeah, doesn't
But
it? If you check a lot of things which are correct according to this pattern, you know how exactly each of them will map to this, right?
so yeah, you are saying maybe you could sample a few positions and check, but then how do you map? It's not very clear actually to me.
So if k is n, there is a 1-1 mapping, right? If k is exactly
Yeah,
n.
these are arbitrary real values, right? In the array.
Oh, okay, got it.
Arbitrary real numbers. It's not a arrays. The range of array is not from 1 through n.
Right, got it.
Right. So
for 2-1, this bound doesn't give anything. The lower bound, this result doesn't give any lower bound. So what is the lower bound then for 2-1?
yeah. For 2-1, the lower bound is omega log n.
Even for non-adaptive.
Even with non-adaptive.
And you can do log n with non-adaptive also. Then.
Yes, you can do log n with non-adaptive. For 2-1 freeness, the known testers are all non-adaptive. Log n query testers.
Okay, thanks.
So then the question is, can we do something with adaptivity for arbitrary patterns? And this is our main result. So this is the context and history of the problem, and our main result is that for every constant k, we can test pi-freeness of patterns of length k on arrays of length n using n to the little o of 1 queries. It's much better than this close to linear bound. Right? So this is the main result, main contribution, main result. Actually. And I hope, yeah.
Is the constant exact, like, is there some value small of 1?
So this is 1 over log n.
Oh, okay.
We didn't optimize for this exponent. Neither did we optimize for the constants here. There is a terrible dependence of k here, sitting here inside, but k is constant. And so this was not our aim. And we believe that, our algorithm itself, when maybe analyzed more carefully, one can even kind of get better constants here, better dependence on K, and maybe push it to even work for non-constant K and still have similar query complexity, slightly non-constant, but not too much. But for all constant K, it's n to the little of 1, and this O tilde notation hides polylog n factors. Yeah. So, and today, so this is our result, and our tester also has one-sided error. That is, by this I mean the following: if the array is pi-free, our tester will always say yes. And if the array is epsilon far from pi-free, with high probability, my tester is going to say no, or rather not pi-free. Are there any questions about the result or the context? Okay. So here are some of the features of the result. So firstly, as I mentioned, it's a strongly sublinear time algorithm. And our techniques are, in some sense, general. They do not depend on the structure of specific permutations that we are testing for. It's a generic approach. So far, the polylog and tester that I mentioned that work for arbitrary patterns of constant length, that tester really depended on the kind of pattern that you were testing for, actually. If it is 1, 3, 2, it's a specific kind of test. 1, 2, 3, it's another kind of test. But our technique, our algorithm is quite generic. And for today's purposes, I'll show an outline of a square root n query algorithm for testing pi-freeness of some permutation of length 4. Okay. And this is already an improvement over the non-adaptive testing, because so maybe I should write here, because so for length 4, every non-adaptive tester must make into the 2/3 queries for same problem. So it's even for the special case, our result is an improvement over the load. And so I said that our tester has one-sided error, and if you did not follow that, it's okay. So, but maybe you can just focus on the following problem for now. I will solve, just maybe even assume that I'm solving a simpler problem, but I'm not. Suppose you are given Oracle access to an array that is epsilon far from being pi-free. Can you find a pi appearance? This is all. So this is what I'll be trying to describe. So consider, some pattern pi of length 4. I'll try to describe a root n query algorithm that will detect a pi appearance with high probability when the adversary is guaranteeing you that the input array is epsilon far from being pi-free. So we'll focus on this simpler, in quotes, simpler problem. It's the same problem, but yeah. Okay, I hope the problem statement is clear.
Yes, yes.
Yeah, you have a question?
No, it's clear.
Okay, so the first fact that we will use is that it's a kind of a folklore fact in generally property testing. So suppose an array is epsilon far from being pi free, then there are many pi appearances that are disjoint from each other. Then there is, or rather I would say, a matching of pi appearances of size at least epsilon n over 4. So I will define what is a matching of pi appearances. And this fact has been used by all algorithms to test pi-freeness, including monotonicity testers. So here, this 4 is because of we are considering only patterns of length 4 for the discussion today, right? It's yeah. So by now, what is a matching of pi appearances? So if you see this array, so here 100, 99, 98, 97 is a 4, 3, 2, 1 appearance, right? Similarly, 78, 77, 76, 21 is another 4, 3, 2, 1 appearance. But these don't intersect, right? They don't share any indices. So we say that this array contains a matching of 4, 3, 2, 1 appearances of cardinality 2. So rather at least 2 4, 3, 2, 1 appearances in this array. So I hope it is clear what I mean by matching of pi appearances of cardinality, or at least epsilon and over 4. Is it clear? Do you have questions?
It would mean that epsilon n by 4 and simultaneously disjoint occurrences?
Yes. So the array is epsilon far from being pi free, which means at least epsilon n values need to be changed in order to make it pi free. So it's a, if you think about it, it's kind of a simple argument. Then you have to somehow, each time you are modifying an array value, you are somehow in some sense killing a pi appearance. Each array value that you modify is useful for killing some pi appearance. So which means that there should be many, at least intuitively, there should be many pi appearances. And that intuition is just formalized here. That's all. So essentially, far arrays contain many pi appearances. An array is being far from pi free. It has many pi appearances, and these pi appearances do not overlap. This is the take home of the slide. Now we are going to, our tester will try to find some of these, at least one among these pi appearances somehow. This is our goal. So we are guaranteed that there are so many of them. Let's try to find at least one. Okay. So the key idea or ingredient is firstly to view the array as a grid of n points in n cross R. So the array indices I am numbering from 1 through 1, 2, 3 up to n. And the range of array is some subset of real numbers. And I do not know this a priori, right? I have no idea what the range is. I have no idea what the array values are. But I'm visualizing it like this. And so maybe I make a query to the ith location in the array. So I specify the index I to my oracle. The oracle returns the value a of I. Then I know that this point is present in the grid, right? A of I is present in the grid when I make that query. This is how I'm kind of learning how this grid looks like. looks like. I'm making queries and figuring out how this grid looks like. But there is some grid that I know. So the first thing that our algorithm does is to somehow equipartition this grid, roughly equipartition this grid into m by m boxes, where m you can think of as square root n. Now, in fact, it is square root n. So you can think of this as square root n. And in the following way. So these horizontal parts, I'm going to call them layers, and the vertical columns, I'm going to call them as stripes. So I will somehow, by sampling, I will make sure that I have an idea of these vertical intervals that roughly equipartition the set of all points in the grid. So the total number of points in the grid is n. By sampling, I will figure out the boundaries of intervals such that each layer has roughly 1 over m fraction of all of the points. So each one of these. Okay, because and some intervals are thinner, they look thinner because there may be lots of points from that lie in the small interval in the array, right? And I also partition the index set into equi-sized essentially subarrays, where each stripe contains n over m indices or points. Okay, so this is my partition. So, and I do this, I promise you, I'm telling you that with high probability I can do this partition. Okay, I think I said all of this. So this stage is called gridding. So I somehow determine these intervals that I call layers, where each layer, each horizontal layer has roughly n over m points. And I also partition, without making any queries, this index set into subarrays of length n over m each. And this I am promising you that I can do this with O tilde m queries. And m, yeah.
One question. Yeah. So how
Yeah.
can you say you do this with sampling, right? So why do you say that without any query? What do you mean by sampling then?
Oh, no. By making queries. Of course, here to do this, I have to make queries. But to do this, I don't need to make any queries.
You mean additional queries? How do you do this then? How do you get these
So
square root n?
here I'm simply considering, the first n over m indices as part of the first stripe. Next n over m indices as that's it. But the layers, of course, I make queries. I'm making O tilde m queries. And m being square root n, I'm making O tilde square root n queries.
Yeah.
And that is within the query budget that I wanted to prove. Okay. And so this gives us some boxes, essentially. This whole grid can be thought of as a collection of boxes, right? It's a cell in the grid, essentially. And I say that the density of a box is the number of grid points in this box divided by the total number of points in this entire stripe. This is the density of a box. In other words, what is the density also represents what is the probability that a uniformly random query made to something here will land up in this box. That's the density of the box. Now, somehow my next high level goal is to somehow approximate the distribution of points among boxes by further sampling. I want to somehow understand which boxes contain a lot of points, which boxes do not contain a lot of points, so that I can ignore maybe those boxes, right? So I want to get somehow how these, get a rough idea of how these points are distributed by sampling. This is my next goal. So here is what I do. So from each stripe, I'm going to sample roughly polylog n, or tilde heights polylog n, right? Polylog n many points, and mark the boxes with at least one sampled point as somehow non-empty. Okay, using further samples. Now, so there are potentially m square boxes, out of which with this technique we can only mark O tilde m boxes, right? But that seems like a big loss to us, because somehow if we ignore all of these unmarked boxes, that seems dangerous to do. Maybe, most of these pi appearances are entirely sitting in these unmarked boxes. But I'll argue that it's not the case, that this is a good thing to do. Here is where combinatorics is going to help us. So the main statement that comes to our help is this famous result of Marcus and Tardosh, where they say that in any grid, consider an arbitrary grid GRR that has roughly more than linearly many marked cells, then it has to contain a pi appearance among the cells. I'll tell you with an example. Suppose my pi is 3214. My pattern is 3214. And suppose this is the, after marking the boxes, this is what I obtained. So just by inspection, I can say that the array contains a 3214. Right? Because any point from this box combined with any point from this box, combined with any point from this box and any point from this box will form a 3214 appearance. Right. So simply because these boxes happen to be marked, I can definitively say that there is a 3214 appearance. And Marcus-Tardosh result tells us that if strictly more than, like if little omega m boxes happen to be marked, then you already have a pi appearance simply among the marked boxes. You don't have to do anything further. You will find your pi appearance among these marked boxes. That is, in any such grid, you cannot mark boxes. It's a packing problem. You cannot, suppose it's, you are trying to mark boxes without creating any such obvious pi appearances. You cannot do that. You can only mark very few boxes. Essentially, this is the main idea. At least the first main idea.
So let's say if I fill the first m boxes in the top, and the second thing I'll fill the rightmost m minus 1.
Yeah.
And third I'll fill rightmost m minus 2 and so on. Then I'm filling approx m square boxes, right?
Okay.
And
it would definitely, yeah.
And in this particular thing, we can't find any path. There are only decreasing patterns we can find. Right?
No, 3214, for example, so you are, oops. So you are saying you are filling this whole thing, right?
No, horizontal.
Horizontally, this one you are filling.
From the top, I fill fill the entire thing here.
Filling this entirely.
Yeah.
Then What are you
In
doing?
the second, I'll fill the rightmost m minus 1. In LM minus 1, I'll fill the rightmost m minus 1.
And then everything else you will fill rightmost m minus 1.
M minus 2, m minus k. In the k thing, I'll fill m minus k.
There will be 4, 3, 2, 1, right? In the like basically you are saying this entire upper triangle.
Yeah.
But there will be, somewhere there will be this 4, 3, 2, 1 sitting there.
3, 2, 1, 4. How will it?
3, 2, 1, 4. Right?
Okay.
Consider the diagonal, for example. So maybe some like the lowest 3 points on the diagonal. Or maybe not the lowest 3 points.
Okay.
The
Got
second
it.
to last. You got it, right?
Yes.
There will be. So you won't have, if you detect a lot of marked boxes, you are in a good situation. If you have a lot of marked boxes, you are in a good situation, you detect. So suppose, so I marked a bunch of boxes and suppose I did not have any obvious pi appearances like this. Then what is the situation I am in? This is the next question. So there is an easy case, that is, you marked a lot of boxes and you immediately detected a pi appearance and you are happy and your problem is done.
So is there lemma constructor, the result you prove, does that say about existence or can you find that existence?
So that lemma is about existence here, but we can actually just inspect and find, right? And we don't care about the time complexity, and because we are not making any more queries. So we can just, time complexity might be large to actually find out, right? Okay. So that is, after marking the boxes, if there are more than, like some constant times m marked boxes, we are done because we would have already found a pi appearance. So suppose we have fewer marked boxes. What do we do? So in that case, can we ignore the unmarked boxes? Still, like, is it okay to ignore the unmarked boxes in the other situation? So we, here is what we prove, after marking the boxes with high probability for each stripe S, it either has many marked boxes, polylog and marked boxes, or if it has very few marked boxes, most of the points in that stripe is contained within the marked boxes. This is what we show. So this is a lemma that we show. It's a property of our sampling scheme. Now, what does this tell us? Firstly, there cannot be too many stripes with polylog and marked boxes. There are, at most m stripes, right? So, and we are marking roughly how many O tilde m marked boxes. So there cannot be too many stripes with a lot of marked boxes. That number will be small, firstly. So we can actually safely ignore all of those stripes without killing many pi appearances. And if a stripe has very few marked boxes, then the marked boxes actually contribute, almost the whole of density of that stripe. The unmarked boxes have negligible density. We can really neglect them. So somehow, what I'm doing at a very high level is I'm trying to get to the kernel of this array. In some sense, I'm trying to eliminate a lot of points from a lot of regions of the grid and really focus on what is the most interesting region, where I know all of the pi appearances are going to lie. This is what I'm doing in all of this stuff. So I'm doing some pruning. This should be the take home from so far.
One question, Nithin. So
Yeah.
you should both these conditions are met in that case, right? You only have omega 1 mark boxes, and also all of them contain a lot of point, right?
So it's an either or. Either there are many marked boxes, or if there are few marked boxes in a stripe, then these few marked boxes actually contain all the density in that stripe. This is what we say. It's a dichotomy.
Okay.
Yeah. So after marking these boxes, what we have is the following.
No, so if there are a lot
Yeah.
of mark boxes, why is it safe to ignore the unmarked? Okay. Yeah.
Because so if a stripe has lots of marked boxes, many such stripes will not be there. There are only very few such stripes by an averaging argument, actually.
Okay.
And it is because of that reason it is okay to ignore them.
Okay.
So essentially we first said that it's okay to ignore unmarked boxes. We will also say that it's okay to ignore boxes with low density among the marked boxes. Again, that will not hurt as much. So finally, we will be able to say that there are big of M dense boxes overall. Interesting boxes, and we have identified all the interesting boxes. Our algorithm has, with high probability, identified all the interesting boxes. Now, among these dense boxes, now let's look at layers and stripes. These dense boxes are spread, distributed among layers and stripes. Now, there cannot be too many layers with more than D dense boxes, because overall there are M dense boxes. There can be at most M over D layers with more than D dense boxes, right? And for appropriate setting of D, we will argue that it's again okay to ignore those stripes also, or those layers also, with many dense boxes in them. So we will ignore all points in such layers and stripes. So finally, we will have this picture that we have a grid with M dense boxes, such that each layer, horizontal layer or stripe, has at most D dense boxes. D is some constant depending on our epsilon. So each layer or stripe has constantly many dense boxes. This is something, it's an averaging argument, and we can say this. And among, in this sub-region now that we are looking at, there is a large matching of pi appearances. We didn't lose out on anything. All of the, most of our interesting pi appearances are in this region. So now where in the grid do these appear? How do these appear? So I will show you maybe one case, and because it's already only 10 more minutes, I'll show you. So since we know that we did not detect pi appearances among the marked boxes, we know that these pi appearances are not just evidently there. That is, they must share layers or stripes. So, for example, this 3214, there are many different types of configurations that they could appear in. Some examples are like this, So if a 3214 appears like this, for example, we will not detect. Because even though this box is marked, this box is marked, this one is marked, this one is marked, simply because they are marked, we will not know that there is a 3214 appearance, right? We will have to somehow go inside and see. Or it could appear like this. Or it could appear like this, Just 2 boxes. 3 2 legs in one box, 1 4 leg in the other box. There are several possibilities for my 3 2 1 4 appearances to occur in the in the grid, in the kind of kernel that we are looking at. These are called configurations. We call them configurations. So a configuration is simply an arrangement of 4 boxes, at most 4 boxes, and a mapping of legs of a pi appearance into these 4 boxes. And we say that 2 boxes are connected if they share a layer or a stripe. And we categorize configurations into based on whether how many connected components these configurations have. For example, this is a 1 component configuration because this is connected to this because they share the same stripe, and this is connected to this, they share the same layer. So if I were to draw edges between connected boxes, this forms one single component. And this is a configuration that forms 2 components, and this is a configuration that forms 3 components. So we can systematically list out all possibilities this way, and we treat them separately. Now, there are only constantly many distinct types of configurations because there are constantly many ways of arranging 4 legs into at most 4 boxes. 4 legs of a pi appearance into at most 4 boxes. So our algorithm actually kind of goes over each of these configurations, so to speak, and tries to detect. So I'll give you one small example. Suppose most of the pi appearances have all 4 legs in a single box. This is one possibility, right? In this case, it's very simple. Then what could you do? Then you could sample a random dense box that you have marked. And that should contain, on average, a lot of such appearances, right? So, since there are big O of m dense boxes overall, in expectation, a random dense box is going to contain omega n over m pi appearances. This is not entirely true. I'm being not very accurate for ease of presentation. Which means I can simply sample a random dense box from among the dense boxes I've determined and query every point in it. And since dense boxes only have, at most root n points within them, I'm only making root n queries. So I've dealt with one particular configuration. There are other interesting configurations. Maybe one more example I can try to give. So suppose most of my, a large fraction of pi appearances are present as in this way. Again, it's the 1 component configuration. All of these are connected, right? But 3 is here, 2 is here, 1 is here, and 4 is here. What can I say? I can say that since at least epsilon and pi appearances are present like this, it means that a uniformly random dense box must contain at least epsilon n over m 3 legs of such pi appearances, right? Because these 3 legs are also distributed. So a uniformly random dense box must contain a lot of such 3 legs. Then somehow I need to figure out somehow the completion of these 3 legs. So let's see how to do that. And that's also not very difficult, actually. So because each dense box belongs to only big O of D cube copies of such box arrangements. Why? Because, so consider this dense box. It has at most D boxes in the same layer. This is something that we had said already. We had argued that each layer contains D dense boxes, each stripe contains D dense boxes. So if I consider some arbitrary dense box, there are at most D dense boxes in its layer. Now each of these D dense boxes can have at most D dense boxes in its stripe. Now each of these D1s can have at most, like it's the number of, essentially the number of such box arrangements consisting of a specific dense box is constant. It's a counting argument. And here we use the property that we don't have too many dense boxes in a layer or a stripe. So essentially now, as I said, a random dense box participates in omega n over m 3 legs. And then I will actually check for all possible extensions of this dense box into this one component configuration, query every point that in this collection of box arrangements, and I'll still be okay. I'll have big O of root n queries. So I think I'm out of time, almost out of time. So there are a few other interesting cases. So maybe I'll just show you one case, one other interesting case.
I have a question.
Yeah.
So these 4 boxes are marked. So why were you not able to identify 3214 pattern at the start itself? Because
they share, so it really looks like a rectangle, right? Just because these boxes are marked, it could be marked by some other points, right? Need not be these specific 4 points, right? Maybe these boxes were marked by maybe something like, maybe these boxes got marked because of these 4 points. And that does not tell me that there is a 3214, right? They're simply marked, but they look like a rectangle.
Okay.
Right. Only if its shape really looks like a 3214, only if they don't share any layer or stripe, only then I can say. Otherwise, I don't know. Otherwise, I have to somehow peek inside to say anything.
But
So
if they are in the separate layers, then definitely you will be able to. What I'm saying is that if these 4 boxes are in different layer, then
different
I guess
layer and different stripe. Yes.
Yeah. Okay.
Yes. Yeah. So these configurations that we are treating at this stage have to share either a layer or a stripe. Only such configurations we are treating here, because they are the more difficult ones. So most of the configurations we can deal with using similar. This is all, and these are all averaging arguments. We can treat, but there are some cases that we cannot. But we have to do some more work. Actually, maybe I don't have time to go into details of that. But one thing I can mention here is that, so here essentially if my configuration appears like this, then somehow what I should be doing is I should look at each pair of dense boxes and test for 1-2 freeness and 2-1 freeness, and then see if there are 4 boxes like this where there is a 1-2 appearance here and a 2-1 appearance here, and combine them to get the 3-2-1-4. But again, so one more subtle point is that if I just combine these 2 dense boxes and get some arbitrary 1-2 appearance, that's not enough. the one leg has to lie in the first box and the two leg has to lie in the second box. Only then it is a valid one-to appearance, right? So it's some sort of a restricted appearance. So we have to, ultimately we end up solving a much more general problem actually, that we are not simply testing for pi-freeness. We are testing for pattern freeness with some specific leg restrictions. This is at least as hard as pi-freeness. So we end up solving a more general problem. So and there are several more ideas needed to reduce finally the complexity to. So I kind of described this square root 10. We have to do much more work to reduce the complexity to n to the little of 1 and also generalizing to larger patterns. So I described, even only gave an overview for patterns of length 4 and that too a specific pattern of length 4 and that too for some simple configurations only. But there are more ideas needed to generalize to larger patterns. But I hope some take home has been there, I hope. So the main open problems, I'll actually scroll to the end. The main open problems are, firstly, the true complexity of testing pi-freeness. We don't believe, currently, we don't believe that our results are optimal. So jointly with Umri, Ben Eliezer and Ilan, we are trying to improve the complexity, and we believe it should be something like polylog n. We don't have a concrete proof yet, but we think it should be possible. And all of our work is for patterns of constant length. What about super constant length? Maybe one can try to come up with lower bounds, right? And a more interesting question, maybe much more challenging question, will be to approximate the distance of an array to pi-freeness or get an estimate of the number of pi appearances. These would be much more challenging questions. Not exactly count the number of pi appearances, but get an estimate of the number of pi appearances in sublinear time, or approximate the distance of an array to pi-freeness. And in the special case of monotonicity, this is equivalent to LIS estimation. So this quest and LIS estimation is already quite challenging to do in sublinear time, or rather the algorithm is quite complicated. So yeah, so these are the open questions. Yeah, and thank you for listening, for your time and for the questions. Again, thank you for having me. If there are any more questions, I'm happy to stay back and discuss or answer. Yeah.
So if the numbers are all integers, is it easy? Yeah, you took real, right? Does it give any flex?
No, I don't think it will be easier if the numbers are simply integers.
They're 1 to n. Is it easy then?
Yeah, this is something we are considering actually. If it will be easier if the numbers are actually from the range 1 through n.
So
yeah.
The lower bound for if the patterns are monotonic, you said it's log n, right? Is there a better lower bound if the patterns are not monotonic?
No, there is no lower bound. Yeah, there is no, there was before our work, there was for general testing, there was no bound node for arbitrary patterns. Neither upper bound nor lower bound. Yeah. Ramesh?
Yeah, so this second question. So where exactly in the proof did we use this constant length? I'm guessing the number of configurations will blow up if.
Yes, exactly. There. Yeah.
Okay.
Because the number of configurations, at least naively thinking, it's k to the power k. And that and more factors of k. In fact, when we do so our n to the little of 1 complexity algorithm is recursive, and each time the distance parameter decays exponentially, like by a factor of 2 to the k or something. But we have only constantly many rounds of levels of recursion, so it's fine, it's still constant. But this actually sits, these huge powers of k sit inside that big O.
So for like very small, like if let's say if k is log star n, like is this still less than linear time?
Yeah, for slightly super constant k, our algorithm is still sublinear time. But we didn't try to optimize.
And did you consider other distance, or is it studied other than Hamming distance?
So in general, in this kind of combinatorial property testing, mostly Hamming distance has been looked at. However, monotonicity of, so this arrays of length and real valued arrays of length can also be thought of as real valued functions over the discrete domain, n, right? So for monotonicity, people have considered LP distances also. And yeah, so it's an interesting question actually, and they show that for LP distances, for in fact, you can get a 1 over epsilon to the power p query tester for sortedness or monotonicity, I think. And there is actually a very, in fact, that paper is worth looking at, because there is a very clever argument that they use to reduce testing monotonicity of real, LP testing monotonicity into LP testing monotonicity of a bunch of Boolean functions. So LP testing monotonicity of real valued functions, they are reducing it to LP testing monotonicity of Boolean functions. And once the functions are Boolean, it's very easy. So now one could ask if some similar argument would work for pattern freeness, but I don't know. So yeah, so the short answer is one can study LP distances, one can study edit distance maybe. Yeah, but for but in combinatorial property testing, mostly it is Hamming distance that has been considered. Any other question?
So if k is very n, as I asked earlier, if k equal to n, this is just testing whether the entire array is monotonic or not, right?
If the permutation is,
if the you want to test whether it's like 5 arrays 3, 2, 1, 4, 5 or not. You're given a 5 array, but you want to check whether 3, 2, 1, 4, 5 pattern is present or not.
3, 2, 1, 4, 5 pattern is present or not. Okay.
Then you can map the entries to say that in the original array, third entry should be the least, second entry should be the second least, first entry should be third least, and fourth entry is fourth least, and so on.
Yes, so it is sortedness.
Yeah, you need to test whether it's sorted or not if it's k equal to n. So
but
is this something you can use when k is large like this?
No, but then, like, how do you define epsilon farness is what I'm thinking there. Is it easy to define? Is it so? 3, 2, 1, 4, 5, free. So if there is so what does it mean to be 3, 2, 1, 4, 5 free for an array? Basically, yeah. Now, okay. Rather, so it's clear what is a 3, 2, 1, 4, 5 free array of length 5. It's clear. Now, what is something that is epsilon far? Okay, so you want to modify at least epsilon n values. No, the point is, suppose you are giving me a 32144. Suppose you are giving me an array that contains a 32145 appearance. I can destroy that 32145 appearance simply by one change, right?
Yes.
I will just change that one to some large value, very large, infinity.
Yeah.
So there is no concept of farness. Like I can.
Okay. Yeah.
Right? Yeah. Yeah.
Are there any other questions? Okay. Thank you, Nithin, for the talk.
Thank you, Rishi. Thank you, Ramesh.